reason is there's a dissipation fence in this room Thursday at this time. So we'll just have an exam upstairs. And if you haven't already signed up for your RC account, I got a bunch of accounts that I approved so far. It looks like 4 of you have associated with this project. Right, so if you did get an approval back from Research Computing and you didn't associate with this project, remember that's one more step you need to do to just complete the account setup. And please try and do this before you leave for break, only because you're going to get the next assignment when you get back from break, and I don't want you to have a week delay when you're waiting for the account to get set up. It shouldn't take them that long to do that, but you never know how it works out with these guys. So make sure you do that before you leave campus. All right. Let's see. One more clarifying thing. Lab is due Thursday at, let's say, 11:59 in the evening. All right. So midnight on Thursday means between Thursday and Friday. Okay. Got that question from several folks. All right. Are only about a half a lecture behind, which isn't bad, according to the so we're doing okay. Any questions on anything we've gone over so far? Nobody's going to ask, what's on the exam?
Can we talk about that at the end of class, maybe?
Yeah, we can go over some stuff at the end of class. I'll just give you an idea about the format. I just have a little bit more material that I want to get through, but then just maybe take an hour or so. Spend the last half hour or so on other stuff. All right, let's see. Some slides. So we're going to move ahead now to Chapter 5. We pushed through Chapter 4, we went through the error analysis last time. And Chapter 5 is a long chapter as far as reading goes, but as you start to read through it, you'll realize that once you get about 10 pages or so into it, it's going to look a lot like radiometry did last quarter. So at that point, that's not going to be the material we're going to cover here. We're going to cover the first part of that chapter, and then going to move on to Chapter 6. Okay, so assuming you have all the radiometry stuff taken care of today. All right. So the part of Chapter 5 that I'd like to go through is the part that has to deal with imaging systems in a very general sense. Okay, we're going to look at. There's so many remote sensing systems out there, right? I mean. If you look at the last count of satellites that's orbiting the Earth, it's up around 5,000 to 6,000 satellites that are in orbit. Not all of them are imaging satellites, obviously, but there's a big handful. Probably we're talking, about 100, sort of numbers of major imaging satellites that are up there, and then aircraft-based imaging systems. There's a whole bunch of those that are flying around, and the designs are just so varied. And if you go to an SPIE conference or an OSA conference or an ICARS conference, any of the remote sensing big conferences that are out there, you'll see 3 or 4 new detectors in every conference that you go to. Obviously, some of these are theoretical. Some are just still in a laboratory. We build sensors here. We've reported on them, and then we've flown them 3 times. Right? So not all the sensors that you see at these conferences are the next big workhorse. But there are some sensors that have been up there since the mid-1980s and are still flying and still collecting data. And so there are some workhorses that are there. But I can't go through all of them. We're not going to go through probably any of them in particular detail. But what I want to do is look at them in a very general sense, so you get an idea of how major classes of sensors operate. And then maybe we'll pull in an example here or there, a specific sensor, to take a look at a particular technology. All right, so obviously the oldest and most tried and true remote sensing systems are traditional cameras with film, right? And even today, A large part of the photogrammetric community still uses film to make measurements with, believe it or not. And as recently as 10 years ago, they were still flying film on the space shuttle, right? So I mean, there are systems that are still out there that rely on film. And why is that?
You get more precision on film, and probably for photogrammetrists, they probably trust like roll error more than they trust like aligning the different spectrum.
The digital images. Yeah. Oh yeah. I would say. All right. So very good point, right? If you have a color system, right? Let's say just RGB, true color system. Most commercial cameras that you have, cameras you have on your phones or your DSLRs or you name it, pretty much any camera that you can afford relies on a color filter array in order to produce color. Well, what that means is you never have red, green, and blue filters or information at the same location on a focal plane. Right? There's some interpolation that goes on. The last thing that remote sensors want is interpolated data, because you want to believe everything. You don't want to make it up. And it turns out that 75% or so of the data that is on a color filter array produced RGB image is fabricated or interpreted. Film's not like that, right? Film still exposes every location of the RG and the B plane simultaneously through the different sensitive layers of the emulsion. Right? It's not without errors by any means, because as you let's see. As you have different layers in your photographic film, there's actually pretty much 4 interfaces that you need to go through. As you have an incoming beam of light, when you hit that first layer, well, you're going to expose your latent image at that location, but you're going to hit particles that are in this film, and all of a sudden you're going to start to get scattered light as you go through. So now this beam might come over here, hit a particle over here, come back over here. It's much like the atmospheric problem that we have in remote sensing. The same sort of thing happens in film. But it's been around a long time. The particles and the design of film has been pretty standard over all that time. And you have silver halide grains. I haven't drawn that picture. I'm not doing it very well. Which are these triangular sorts of silver halide sorts of molecules that are sensitive at these locations. They've gotten smaller. They've changed shape a little bit over time, and as the chemists figure out how to make a more sensitive emulsion. But in general, the size has stayed about, it's changed a little bit, but it's stayed pretty constant. So the scattering properties haven't changed all that much. But that all being said, you still get a better co-registration of red, green, and blue on film than you will in any digital system that relies on a single focal plane. Right? Now there are other focal planes or other designs that you can use in sensors where you simultaneously expose, let's say you're doing RGB imagery again, you simultaneously expose the red, green, and blue on 3 separate focal planes. One that's filtered for red, one that's filtered for green, one that's filtered for blue. But then, as Maria said, you still have the problem of re-registering those focal planes. You can do as much as you want in the laboratory, right, to get those things as aligned as perfectly as possible. But the minute you put it in an airplane, on a helicopter, on top of a big rocket, and launch it, what happens to these things? Right, everything starts shaking, and I don't care how good you were when you made this thing mechanically, you're going to have misalignments that come into play. So you always have to re-register your data. So photogrammetrists hate the fact that you have to do something to your data before you start making measurements on it. Radiometric remote sensors hate the fact that maybe you don't have perfect registration for all the colors that you're looking at for a pixel location. So, man, I forgot where I was going. How did we get off on that track? I asked a simple question.
So why film?
So why film? Okay. All right. So that's one reason. The other reason is we still don't have an electro-optical system that has as good a resolution as film does, right? So one of the first projects I ever worked on when I started working for the Beers Lab a long time ago was to take photographic film and scan, and I had to write a piece of equipment controlling software to run a microdensitometer, where we actually took the piece of film, put it on a light table. The light table would scan. There was a microscope objective that illuminated, and another microscope objective that picked up the. I should just draw pictures on that. So we had a microscope objective over here, and a microscope objective over here, and a source at this location, and a detector at this location. So you're able to focus light down very small, down on the order of a couple microns, right? And then look at that same illuminated spot and get all your energy out to a detector. Right? Then you had a piece of film that you placed in here, and this was on a mechanical stage. Just draw like kind of a screw drive here in the X and Y direction, so you're able to move the film in the X and Y direction in a raster format and able to scan out and digitize the image. So much like you would in a scanner that you might have on your desktop today, if you have one of those 35mm film attachments, you can actually scan it using a line scanner. Well, there, I don't know, if you have a desktop scanner, how many pixels is it across? I don't even know if we think about that anymore. It used to be a big deal. I don't even know. I'm guessing probably about 8192 across. Right? That's across an 8-inch area. Right? So you're talking about 1,000 pixels per inch. It's not a lot. Still, that's not great resolution when it comes down to when you think about photographic film, where you might have particles that are down around the size of 4 microns or so. You still can't get down to that with typical scanners. But something like a microdensitometer, I don't know if that's a common term anymore. Essentially what you did was you just measured the density of the film at this point, right? Or essentially the transmission, and then converted that into digital counts. All right, so I went off and I wrote this program. It was awesome. This I don't think we have the machine anymore. It was located down in Zorn-Lincoln's detector lab. It might still be down there because the thing weighed about 6,000 pounds, right? It was a behemoth. It was probably twice the size of this podium wide, and the light table was only about this big, maybe a foot by a foot. Then it had all the gears and stuff on it. Why was it so heavy? Stability. You didn't want this thing to shake as it was moving. Because when you're talking about measuring down on the order of 4 microns, if you have any mechanical vibrations, now all of a sudden your spot's moving all over the place. When this building was actually built, one of the cool things about Zorn's lab, if you ever get to go down in the basement and go into that laboratory, you'll notice that the floor is sort of disconnected from the rest of the building. There's a seam. It's actually vibration isolated from the rest of the building. So the entire room is vibration isolated, and then you had this 6,000-pound instrument sitting in there to isolate the vibrations. And so we were able to take very accurate measurements like that. Downside, and this was probably because of me, but this thing took about 24 hours to scan a 9-inch piece of film. Right? It's a 9-inch piece of film. That's a big piece of film. But if you're talking 4 microns per pixel on a 9-inch by 9-inch piece of film, how many pixels are you talking? Lots, right? More than you'll see in any image that you're seeing from any video system. So it's a neat technology. It's still used in very, very I would say sparse cases, but where resolution is incredibly important. These kind of technologies still sit out there. I'm going to walk downstairs after class and see if that machine's still there. I'm wondering. All right, so film has that resolution, and it's well understood too as far as calibration goes. Right? This is something we don't show you anymore. You two might have seen it in MVP over the summer.
D-log
right?
H groups?
D-log H group? Yeah. All right. So, film was awesome. Now I got to get this right. Density, right? As a function of log exposure. Right? These were a plot that for every photographic film in every canister that you bought from Kodak, you would get a little information sheet that would give you this curve, and it was a curve that had a sigmoidal shape to it, and it was the response or the density that would get produced on a photographic film based on the exposure that that film received. Okay, and exposure, if you remember, H is the integral of what? The irradiance onto the surface as a function of time. Okay. Or, you know, it's often just written as the irradiance times time. And this is, if you processed the film at a certain temperature with a developer that was mixed up, you know, precisely according to the chemical formula that it was supposed to be used, this curve would come out, you know, more often than not, exactly the same way that Kodak wanted it to be. If you developed a little longer or your temperature was a little off, then this curve would shift. But what you were always able to do, if you had a roll of film, let's say it's a roll of film, and you have exposures here, and here, and here on that film, well, in the beginning of this film, you were able to go to something called the sensitometer, right, and actually put an exposure onto this film in a very calibrated fashion. You had a mistraceable lamp over here. You had a density wedge that went from very dark to very light on the other end. And you would place a piece of film right in contact with that and put a contact exposure onto that piece of film. Right? So you knew the energy coming from this light. You had a shutter in here. It's a rotating shutter. And it was very precisely mechanically calibrated. Right? So you knew exactly the exposure time that you had for this. You knew exactly the exposure for this step wedge that was in here. So you knew, density. So then you knew exactly the exposure that would be on your film. You were able to then develop this with your photographic process. And the neat part was, is your other exposures were on that same piece of film. So even if you got the processing a little bit wrong, and this curve shifted one way or the other because temperature was off or you mismixed your chemical, you had this step wedge over here that you can plot this curve from directly. Right? So you had built-in calibration every single time you took a photograph. So every time you would go up in an aircraft before you took off, you would take your film, you'd roll a little bit out in a dark room, you'd expose it with one of these sensitometers, you'd put it back in your camera, you'd go fly your mission, you'd come back, you develop your film, and you'd have perfect calibration every single time. All right, so I sort of missed film, about that much, right? Because it was a pain to work with. You had to get back down on the ground. You had to develop your film. You had to make prints. You had to do all this stuff that took time. And you know, now I could go upstairs. I could ask Jason to go fly our wasp sensor. He drives over to the airport, puts it in a plane, goes up in the air, and in real time I have imagery coming to my desktop. Right? So that's hard to give up. But calibration becomes a whole other problem. Right? So there's definitely trade-offs between these two sorts of systems. So, like I said, this is one of the cameras that was just filmed recently on the Space Shuttle. This is a large format camera. So the film in this, you know, you're talking about a foot by a foot for each exposure. Beautiful negatives to see if you've ever seen them. And you can get, you know, really high sorts of spatial resolution. So here's what we were just talking about. This is, you know, color film. You can go on that piece of film and expose a step wedge. And, you know, they look something like this. And you would go and you would measure each of these densities, and you would plot the log exposure for that exposed each of these patches on the film, and you plot density over here on your y-axis, and you'd have perfectly calibrated imagery every time. Now, as times moved on a little bit, we started to digitize this stuff. Well, that was great. So you can go ahead and digitize this, use the microdensitometers I had downstairs, and do that sort of a thing. And you can also digitize your step wedge, and now you can have log exposure related to digital. So you had a calibration now that you were able to transfer to a digital system. So it made a very nice transition from film to digital. Now, we've eliminated film pretty much from most systems at this point. So what we're missing is this calibration step. In many electro-optical systems, this is totally gone. And this is one thing that if you're ever looking at a system that you're going to do remote sensing sorts of applications with, you want to ask that question, what kind of built-in calibration is available? It's very hard to do that now, right? If you don't have that ability to take that media, that film, take it into a lab, expose it, and then have that present on the same media that you were developing once you landed, and looking at the imagery afterwards and being able to calibrate that imagery afterwards, if you don't have that every single time, then you always question your calibration. Right? If you have an electro-optical system and you calibrate, you can still calibrate in the laboratory. I could take a system into the lab, I could point it at an integrating sphere that has a mistraceable lamp in it, and do you guys have a lab in radiometry where you use the spheres? Talk about spheres? Okay. We have, upstairs, we have a sphere that has about a 10-inch opening on it. So the sphere itself is about this big. Beautiful, beautiful uniform illumination source. So we could put up to a 10-inch aperture in front of this. So that pretty much covers any of the remote sensing systems that we have here. And you can then turn on multiple bulbs in this, right? So there might be 10 bulbs inside of the one sphere that we have upstairs. And a combination of those bulbs can give you different levels of irradiance leaving that sphere. And you could then know as a function of irradiance what the response of your electro-optical system is, right? So very similar to what we've done here with film, but now we can do that in the laboratory. But the question always becomes, what happens to your electronics, right? As your electronics get put into an aircraft, they get taken up in the air, they change temperature, they're on for 3 hours at a time, do they drift, right? Do you have a change in calibration as a function of time? And the answer is almost certainly yes, right? So being able to calibrate in a lab like we can do upstairs is good, but you don't have a calibration essentially for every shot that you've done. So built in or built on board calibrators that are present on the actual detector itself are the most sought after sorts of systems, I guess is the best way to say it. So if every time you shot a frame, imagine that you can also get some calibration data at the same time, right? A known lamp, a known illumination source, right? So you know the exact radiometric output of that source, and you record what your sensor sees every time. Well, that sounds great, right? But now that means on your sensor that's being thrown around on a tarmac and being bolted into an aircraft or put on top of a rocket and shot into space, you have to have a very precise and traceable lamp. Right? What's inside of most lamps that make them glow? Right? The filament. Right? You ever take a light bulb when it's on and you start to shake it? Oh, you got to do this. Right? Take a light bulb and start to shake it, and the filament will actually mechanically start to shake. The filament's always shaking when it's on, but you could shake it, and it'll start, and you'll see variations in the light source itself. We see that on board calibrators all the time. So then maybe use an LED, but now you don't have the spectral source power distribution that you would have from something like tungsten. So there's all kind of problems about onboard calibrators, but we'll try and do our best, and we'll talk about some systems that we use to do those kind of things. All right, a little sidetrack. If you ever have a light bulb, a tungsten light bulb, we won't have these for much longer, right? Are we becoming illegal January 1st? Right? The 100-watt light bulbs illegal January 1st in California, I believe. Really? Yeah, I guess. And it's a state decision, right? So South Carolina has already said we are not going to obey the national laws about incandescent light bulbs, and we're going to continue to make them. So the residents of South Carolina will have light bulbs from this point on. If you drive that across the border, you committed taking an illegal substance across the border kind of crime now. Right, so stock up on light bulbs before January 1st. I don't know what New York's going to do. All right, where was I going? All right, so if you ever have an incandescent bulb burn out, right, you see that big flash and it burns out. Take the light bulb and put it back in the lamp, turn it on, and start shaking it, and eventually the filament will hit and it'll reconnect, and you can get your light bulb back. I do that all the time because I'm really cheap. Right? And when more times than not, I can get a light bulb back by doing that. So you should try that out sometime. All right. All right. So once you, all right, let's talk. Let's go offline here for a sec, and let's talk about throughput. the system. All right, let's figure that out. All right, now let me ask you, I don't want to review this heavily if you've already seen this, but let me know if you did. Did you go through a concept called, I guess throughput would be the name it was described under, but the term that would come out of it was something called G number? Okay, so you know G number. All right, so let me just talk about the more interesting parts of this then. All right, so if I have a simple optical element, right, and I'm focusing the energy down onto my focal plane, and I place some sort of detector material there, whether it be film or a CCD array, whatever it turns out to be. The irradiance onto that surface, I'm going to go to my notes here so I don't get it wrong, in the end comes out to be something like this, right? The irradiance onto that surface is the radiance reaching the sensor, so L, which is at the front end of the optical elements, times pi times d squared over 4. I'll just build this up a little slowly. All right, so that's essentially the area of your aperture, d squared over 4, times the focal length squared. Focal length is here, if your object is an infinity. All right, and then we have one more term up there, which is the transmission of the optical elements. Okay, so the G number portion of that is what we call 4 times the F number squared tau pi. And if you remember, the F number of an optical element is focal length over diameter. All right, now, this is true, and this is probably the form that you saw in radiometry. All right? This is true when you have a refractive optic. All right, a simple hunk of glass that's bending. That's refractive. There you go. That's good. All right. But that G number, or that camera equation, is going to change a bit when we start to look at most of the systems that we're going to use in remote sensing sorts of applications, right? Because it's not often that we use an element of glass in front of an optical system, or as an optical system for a remote sensing system. Why is that?
Is it because of the change in temperature on board?
Oh yeah, change in temperature on board. This piece of glass starts to expand and contract. You definitely have problems with that.
And the infrared will not go to.
Infrared doesn't go through glass, right? If you're looking at long wave infrared, it does not transmit through glass, right? So there's issues with that. Other issues though. What's the limiting factor on the resolution that you can produce with an optic? Remember something called the Rayleigh criteria? Wait, you're all in optics now. No. Some of you are in optics now. All right. I don't want to get the equation wrong, so we go to the source of all knowledge, Wikipedia. Well, go to Google first. Just get the. Okay. So essentially, if you're thinking about an optical system and you want to know what's the best resolving power, right? What's the finest detail you're ever going to be able to see? Right? How do you figure that out? Well, it's this equation right here. Delta L is going to be the angle, and the smallest angular separation that you'll be able to make between adjacent scene elements. So if I have an object, let's say a basketball sitting here and a basketball sitting here, separated by a basketball lip, sitting on the ground. If I want to be able to see those basketballs, how do I need to sample that in order to assure that I can see the different, be able to resolve those? Well, if I had an angular field of view that could see a basketball, that means I could have an angular field of view that could see the space between them, and an angular field of view that would see the basketball. Okay? And so, what's called the Nyquist limit Roger couldn't have done a class and not mentioned Nyquist limit, right? All right. All right, so the Nyquist limit says that I have to have twice the, right, I need to be able to see, twice the width of what I want to check out. That's a bad way of saying it. I need to have 2 field of views for every field of view that I want to see. Right, just to put it in layman's terms there. All right, so that's delta L. All right, what's it a function of? It's a function of the focal length of the lens, the diameter of the entrance aperture. What is that? It's the F number, right? And the wavelength of light times 1.220. The constant that comes in here. All right, so if that's the case, do a simple calculation, right? Just run off and do this calculation on your own. Take a wavelength of green, right? 555 nanometers. Put it in whatever units you want to do it in. Let's do it. All right, so 1.220 times, pick a focal length for a lens that you might put on a remote sensing system. Just pick a number. Let's take 1,000 millimeter lens, right? All right, millimeters. How many meters is that? It's a meter.
1 meter.
All right, so let's say we have a meter focal length. All right, and 555 nanometers is 0.555 microns, so 0.555 times 10 to the minus 6 meters. And, all right, let's figure out the diameter of a lens. How big of a thing do you want to see on the ground? Whenever you hear somebody talk about remote sensing and spy satellites and all that, what's the example people always use? You guys don't read enough spy on. You always can, all right, they always say you can read a license plate on a car, right, from space. Right. First of all, license plates sit like this, right? Satellites look like that, right? So it makes it hard. But let's say we have a satellite that was looking this way, and we can see the license plate. What sort of resolving power do you think you need to read a license plate? How wide is a left on a license plate, roughly?
2 inches, 3 inches.
Oh, but a line, right? Because you want to be able to see the letters, right? So let's say you had a D, right? The D is written like that. How big is that? Because you need to be able to start to see things like this.
1 centimeter?
Yeah, let's say a centimeter. Right. So, all right. I don't know what the side story thing is here today, but so my wife parked her truck over at the gym parking lot the other day, and somebody came around the corner and like scraped her entire front bumper, and took the license plate off and fell on the ground. Scraped the whole thing up, and you should meet my wife sometime. She got very angry about this. And so she calls up campus safety, and campus safety they got all excited because this was something to do. We're going to pull all the surveillance footage, and we're going to get back to you. So they saw it happen. They saw the car hit the front, and they said, oh, but we can't read the license plate. I said, well, you're into imaging, right? Could you enhance it? Because they could do that on TV all the time. All right, so needless to say, we wound up paying for the fix on the car. All right, so let's figure out what we would have to do in order to that. So centimeter. So that is 1/100th of a meter? Metric
Yes.
system still has it.
Yeah.
0.01 meters. Anybody have a calculator?
So it's not a delta L, it's not the angle, right?
Oh, in this case, it's not the angle. That's right. This is in. You
Right.
could do it. You could do it either way. All right, because we're talking such small angles, it does work out. The distance will work out. So this will give us something close.
So this is
Not
like,
exactly.
This is like more the distance between the two basketballs.
Yes.
right?
That
And this is actually what I have to be like in the order of the wavelength, right? Like,
right. But in this, yes. So we also. All right. So let's see. What are our units? These units cancel out. So this is a unitless quantity. So this has to come out in an angle. Right. So we should. I mean, small angle approximations will get us close here, but let's say let's figure it out exactly.
but it's not cancelled out actually, right? Because this is like centimeters square and this is centimeters.
Why isn't there
Oh yeah. Wait a minute. Yeah. So this is meters squared over meters. So we're still in meters.
Yeah. So delta L should be in meters. right?
Yeah, this should, okay, so this should work. All right, so,
I don't think change in L is the angular resolution. I think above was the angular resolution. This is the spatial resolution.
this is a spatial one.
Yeah.
This one's the angle one.
Yeah.
Yep, you're right. All right, so, calculate. I can do math. All right, so 1.22 times 0.00005. 0.555. That look right?
Yeah.
All right. So that equals that, and we got to divide. Let's see. Divide that.
Multiply by 100.
Like 0.0.
Multiply by 100. All right, so what do we wind up with now? We got to take the reciprocal of that, right?
No, because you just switched
No.
from 0
Wait,
to
no, did I
0.
just switch?
Yeah, that is the.
All right, that's D. That's not D. That's D. But that's in meters.
So that's the aperture size.
Yeah, no, that's not right.
Maybe you got like more zero.
Oh, it shouldn't be 0.555 times 10 to the 36. Should it be 555? Oh, it's like mathematics, yeah.
Yeah,
okay,
so that should be the same. Got 1,000 millimeter lens. I'll come back with a better example. I'm doing something wrong here. Probably the focal length that we chose. Could be. Let me come back with a more realistic example. What I have an example back in my office of taking Hubble and essentially swapping it around and looking around and seeing what the best resolution we can see. But you know, it turns out, just from having done this in the past when I was prepared, you're talking lenses, a refractive optic, on the order of 20 feet across. Right? That's a big piece of glass, right? To even begin to fathom grinding.
You mean the diameter is 20,
Yeah.
20 feet?
Yeah. To be able to read a license plate. All right. So to do that sort of a thing. So you're talking what? Half the length of a school bus, sort of lengths in glass. Grinding that is almost impossible. Launching that without cracking it, definitely impossible. Right? So there's issues that come up with refractive optics. Also, going back to the issue with color not being aligned in the case of some electro-optical systems, what happens to color going through glass? Yeah. What happens to your where you come to focus, right? Some wavelengths will come to focus back here, some wavelengths will come to focus up here, and only one wavelength is going to come to focus on the focal point. So you wind up with photonic aberrations because of that. You come up with misfocus because of that. All right, so there's a lot of problems with glass. So to get around that, what we tend to do is we go with reflective optics. So there's a lot of different reflective optic designs that are out there, and they all have some good points about them and some bad points about them. So let's take a look at some of them. One of the easiest systems to propose is an off-axis parabola, right? Where we have a parabolic mirror that takes parallel rays coming in from infinity. Most remote sensing systems are so far away that we consider all our rays coming in parallel to one another. And they come to focus somewhere off-axis. Okay? What's the problem with this kind of a system? Right? This looks good, right? One reflective surface comes to focus off here. But the problem is that the focal length for these systems dictates how big the actual optical system needs to be. Right? Because if you want a 1 meter focal length, the only way you can do that with this sort of a system is to have the distance from this mirror to here be 1 meter. Right? If you want more than 1 meter, it has to be larger. And that's the kind of focal lengths that we're talking about in a lot of these systems. So this forces the size of your system to be very large, at least the optical portion.
So the focal length should be like the distance between the object to the almost like the camera, like.
No, the focal length will be from your focusing optic to your focal point. Right, the distance between where everything comes to focus. So if your focal plane was to be positioned right here.
But
right.
what I wanted the object will be there, like in this distance.
Oh, the object will be somewhere
Right,
here in
infinity.
infinity. Okay. So be several hundred meters.
So
or
the
100
detector
kilometers.
should be there.
The detector would be here, off axis. So we need big systems to do this. Ideally, we'd love to do this all the time. When we do things in the laboratory, when we make instruments in the laboratory, this is a design we use often. I actually have a collimator upstairs that we designed this way, where we put a light source at this location, so we use it backwards, and we can produce rays coming from infinity. So if we want to calibrate a remote sensing system, we want to simulate rays coming from infinity. If I put a niche traceable lamp at this point and have a parabolic off-axis mirror, I can then produce a collimated beam that can fill my entrance aperture system. So this is great for calibration systems. It would be great for real systems if we didn't have size limitations, but we always have size limitations. All right, so one of the next things that you can do is use something like a Newtonian design for your optics, where you have a primary mirror and then an optical flat mirror that takes the rays coming in from infinity that are again parallel, focuses them through the fold mirror down onto a focal point. All right, the actual focal point of that primary mirror is sitting right over here. Okay? But if we had to put our detector at that location, we'd be right in the middle of the optical path. Okay? So we can put a fold mirror, which is still right in the middle of the optical path, and take that outside and place our detector outside here. Well, this small mirror is less of an obscuration than if we had to put all our electronics in our detector at the center there. A lot of your electronics are typically located very close to your sensor. So we'd wind up blocking more of the field of view if we placed the detector at that location. All right, well this is a good design. But again, it's fairly long as far as its focal length goes, because your detector would physically need to be here, okay? And that has to be the focal length away from the primary mirror. You can fold it out But this fold mirror has to be pretty far away because your beam has to converge enough so that this mirror could be small and not block your entire field of view. All right, so you could move this closer, but then your mirror needs to get bigger. So the Newtonian design, while it's a good one for amateur astronomers, right? And these are nice, cheap, reflective telescopes that you could buy. They work great for that. If they're a meter long, they look kind of cool when you're using them. So that's nice. But when you want to make a small compact system, this one's a little too big again. Yeah.
So why not to use the primary mirror with smaller focal length?
Bend it more. Bend this mirror more so the focal point comes in closer.
Yeah.
What happens then? You get a lot more aberrations, you get a lot more cost of production, and your focal length's smaller.
What is the problem with the small focal length?
All right, so if you have a
If you
small
want a
focal
compact
length,
system.
what's that?
If you want a compact system,
If you want a compact system and you have a small focal length, that means you can't see with a lot of spatial resolution on the ground. Right? Because when we go back to that Rayleigh equation, one of the factors was the focal length. You need a long focal length to be able to see smaller objects. Just like in conventional photography, when you zoom, right, you can see more details. It's because your focal length cut off.
so it's the like trade-off between the focal length and the diameter.
Yes. You can build up your resolution again by increasing the diameter of the lens, but now you're talking about making a shorter focal length, more highly curved surface with a bigger piece of glass, so that drives the expense and the weight of the system layout. So everything about sensor design is a trade-off. All right. One of the most common used designs is something called the Cassegrain telescope. And the way this one works is, again, you have your rays coming in from infinity. They get reflected off a primary mirror. They get reflected off a secondary mirror here. And if you see, this mirror here is typically parabolic in shape. This one is typically hyperbolic in shape. And there's usually a hole in the center of the primary mirror so that you can take this ray and focus it back through that hole and place your detector behind the primary. Right? So what you've done here is, if you wanted a 1 meter focal length, you can now fit that in about a 1/2 meter area. And so you cut your size constraints down by a factor of 2. So these kind of systems are nice, but they tend to have, in this case, a lot of aberrations due to the curvature of the mirror surfaces. So these are.
How do you suspend those secondary mirrors?
What was that? I'm sorry.
How do you suspend them?
How do you suspend them? All right. Yeah. How do you suspend that mirror in the middle? Right. Usually, you do that with what they refer to as a spider web. So if you're looking down the front of the telescope, right? So you're looking. This is looking down the barrel of the telescope itself. You'll see the secondary mirror in the center there. Usually they try and do this with as few as possible, but if you take 3 wires and you bring them out to the edge, you suspend it there on those 3 wires.
So you now have the obscuration of your mirror and the wires.
Yes. Yep. These produce problems. This produces a problem also. But what you gain is you gain less weight because the assembly is smaller and a more compact size. What you also get is some aberrations. Right? You can make these, both surfaces, both the parabolic primary and the secondary, you can make them both A-spheres, right? And correct all the aberrations, but now you're talking an incredibly high manufacturing cost. Now, the nice part about remote sensing system is typically you build one, and you have a $10 billion budget to do it. You have a big budget to do it. I don't know how big. You have lots of money to do it. So making one good optical system, is a possibility. All right. Now, there are more Go for it.
Just on the cascading.
Yep.
So I know on like backyard telescopes, you have to collimate them frequently enough that, because the secondary mirror gets kind of shifted.
Right.
So how do you do that in a remote sensing?
You make it rigid, so it doesn't
Really,
shift.
really?
Yeah, those wires are very, very rigid in remote sensing systems. And you deal with them when they go out of focus, right? So yeah, I mean, as long as you can predict what's happened to this, as long as you can model what happens to that mirror, you could do geometric corrections afterwards. It's not what you want to do, but you can live within some condition. But you have to make that as rigid as possible. Right? These TMAs, or these trimirror anastigmats, if I can say that correctly, these are great designs. What these allow you typically to do is have a wider field of view. These tend to be very narrow field of view cassegrains, and these tend to be more wide field of view. So if you do want to do a wide field of view sort of a system, you can go with these sorts of designs where you have 3 mirrors, right? Primary, off to a secondary, off to a fold, off to a tertiary, down to your focal point. The nice part is no obscuration. So these are good systems, but now you're keeping 3 mirrors aligned as opposed to 2 mirrors aligned. So it gets to be a little bit of a harder problem for exactly the reasons you said. All right, so these are some of the common optical designs that are out there. This one by far is the most popular. What I mentioned before about a modification to make those surfaces A-spheres, that takes a cassegrain which is the combination of a parabolic and a hyperbolic mirror. When you make the parabolic mirror and the hyperbolic mirror A-spheres, it becomes what's called a Ritchie, let's see, Cretan. I'm going to get the spelling on that one wrong. A Ritchie Cretan design. I don't think that's the way you spell it. There's Yeah, I've seen it before 100 times too. I can't remember how to spell it now. This is when both of the mirrors become A-spheres. Right? That's expensive. Then there's another one. What was that one called? A Dow Kalman, I think is the name. I think it's a Dow Kalman design. And in this case, you just take the parabolic mirror, the primary, and you make it an A-sphere. You leave the secondary, the hyperbolic mirror, as just a standard spherical lens, and you get rid of some of the aberrations. All right. So this one is a nice middle cost. If you don't have enough money to make both of them A-spheres and make a Ritchie Cretan, you can make a Dow Kalman and just make one of them A-sphere, reduce the cost quite a bit, get rid of a lot of the aberrations. So this is sort of a trade-off between a cassegrain and a full Ritchie Cretan sort of design. So, like I said, if you're building a sensor at a university, we use those and deal with the aberrations. If you got government dollars, you build one of those, right? And if you're a company like Worldview, and you're trying to make a commercial enterprise out of this, you probably use one of these. So it depends on how much money and how much fun, or what the absolute purpose is, right? You got to take that into account too. Because if the system you build doesn't have the sort of resolving power that you need to solve the problems that you want to solve, then you waste all your cash anyway. So it's always a trade-off when you're building these things, and you guys are always going to go back to your management and say, I absolutely need this. And they're going to say, well, I don't have that much money. And then you're going to have to make your case to them. So keep these kind of things in mind. You'll learn a little bit more about these designs and optics, and you'll be smart enough to make your call for it. Doesn't mean you're going to get your funds, but at least you can make a good story. All right, now, the problem, though, comes in with the G number, because we wind up having a bit more obscuration in the way, right? So if we go back my picture for a minute, we have this area that's being blocked. right? So now, we've gotten rid of the glass, so we don't have the transmission through a glass loss, which is good. If we have very nice first surface mirrors everywhere, our optical throughput's going to remain very high. But we're actually blocking a portion right here of the diameter of the entrance aperture, and whatever supports that we built into place to hold that, blocking those also. Right? So it turns out, just go wrote this down before I came down here, that the G number in this case is going to look very similar in form, except the way that they presented it. They just multiplied through the top and bottom by 4. But in this particular case, our G number is going to be 4 times the F number squared over what John breaks down in his book is 2 different transmission factors. Pi. All right. So tau sub L and tau sub S are the losses due to the optical properties of the material, so transmission, or in this case reflection, so any loss due to a non-perfect reflection. And S, tau sub S, is the loss due to the area blocked by that central primary pair. Or I'm sorry, the secondary pair. So the tau sub S term, in this case, is 1 minus, 1 would be perfect, right? So we gotta subtract away the portion that's blocked by that center. So what's the area of the secondary mirror? Well, it's pi d squared over 4, where this is the diameter of the secondary mirror, divided by pi d squared over 4 for the primary mirror. And so d sub s and d sub p in that case. So everything cancels out there, and we get 1 minus diameter squared for the secondary and the primary.
You should take like the solid angle, right? Like it goes to this, but the area would be larger than, because there is some distance between the two, right? So you block a solid angle.
But it's an infinity.
No, but the distance between the two are not infinity.
No, the distance between the two is not infinity.
Right.
But all your rays are coming in parallel to one another. So the only thing you need to block by is that section of area that's in. I agree with you if you're focused closely. But in this case, this is just serving to block the rays that are hitting in those, like that location right there. Everything else is still gathered. If these rays weren't coming in parallel, you'd be right. So you just have this extra loss term. So what's the idea? Try to make that as small as possible, right? How do you make it small? You move it further away from the primary, but that makes your system bigger. And so where you place that secondary, right, you have to weigh off the amount of loss that you're willing to deal with, because it needs to get bigger if you move it closer to the primary, versus how big you want to make your system. Right. So, putting all this together, just so you have an idea of what's happening, there's lots of different ways we can put together a system, and we're going to look at systems in more detail after the break. But here's the optical system that we're just talking about. So here's a Cassegrain telescope. Right? And for an electro-optical sort of system, we'd have that Cassegrain focus onto a detector. Right? That detector has some sort of preamplifier that takes the data that we're getting from the detector material itself, hopefully through a fairly low gain, fairly low noise sort of process, gets the signal up to a level where we can run it through some sort of conditioning electronics, some sort of conversion to voltage. Right? So maybe we can get a 0 to 1 volt or a -5 to 5 volt sort of system coming out at this point. Then we can do a lot of things. We could record voltage on an analog recorder of some sort, land an aircraft, come down, do an analog to digital conversion, convert that to a digital image, reconstruct it. and then do our image analysis. And that's one way of doing it. It's the way we did it for a very long time. We actually just threw out our last tape recorder. We used to record these on big 24-track Ampex, professional recording sorts of systems in the aircraft. Worked great, but you had to land and you had to do all this post-processing. Well, the other way is you could through some sort of radio link, take that data right down to the ground, record it, go through the same A to D. It's still slow. More conventionally, what we do now is go through an A to D converter on board, right on the aircraft itself, record it digitally, and then land and pre-process data. So this recording in this particular case is some sort of hard drive, some sort of digital media. Or we do this with our WASP sensor. We can take the A to D on board, take that digital signal, send it down to the ground via an RF link, and then record it directly on the hard disk and go through the rest of the process. So these two paths on the left-hand side here are the most common that we do currently. Not to say that we don't do this one still, but most of the time we're doing this one in the middle, where we record on board, land the aircraft, and post-process. That's probably still the most common system that is used. Obviously, if you're collecting on a satellite, you could record on board, or you could direct down transmit. And the problem with the satellite, well, what's the problem with the satellite? Why would you want to record on the satellite before you send it down? Yeah, you might. That's right. Your satellite's rotating around the Earth, and there's times where you're not going to be able to see your downlink station, so you need to record and send it. Or the other choice is to use relay satellites, so you can bounce off a couple satellites and get a direct down. All right, now if you ever are fortunate enough or unfortunate enough, depending on how you look at it, to use a film camera again, there you really don't have a lot of choice. You got to bring it down to the ground somehow. Either you throw the film out of a satellite and catch it with an airplane and bring it down, or you just land your plane and bring it down. And then you have to process your film, take your latent image on your film, process it, go through a calibration step, and digitize that with something like a densitometer, and you wind up with the same analysis point with your digital analysis. All right, so we'll look at this flow. We'll look at a couple systems that do this sort of thing after the break. And see some of the details about how this all works. All right, so we got, let's see, it's 5 after 11 or so. Let's talk about the exam a little bit, just to alleviate, hopefully, any worries. All right, so here's my worry. I'm doing this class for the first time. Whenever you make up a test for the first time and give it to a class, you wonder, is that too long or is that too short? Right? I think I got it right. There's 5 questions on the exam. I'm guessing one of them will take you about a half hour, and then the other 2 maybe 15 minutes or so. Okay, so that should give you plenty of time. At least that's what I'm looking at. Question was asked earlier in the quarter. Are these going to be, plug and chug type problems, or are they going to be derivation type problems, or what sort of problems are you going to ask? And I said, I don't know, because I haven't made up the exam yet. Well, I made up the exam now. So I really want you to understand how all this comes to be. So derivations are probably a good thing, right? I mean, when we looked at photogrammetry, we did some simple right angle geometry, and we were able to derive some photogrammetric equations. That sort of thing's fair game. We looked at radiometric treatment of energy, right? So we derived the big equation, or we came up with the big equation. The big equation is something that I want you to fully understand, right? That's really what this whole course is about, is that one equation, radiance, region, and sensor. So if you can understand all the terms in there, come up with those terms on your own, right? Be able to derive, put together that equation. Just think through that picture of all the different paths that get photons from the source, or from the sky, or from the target to the sensor. Okay? Think about all those paths. As long as you have those in your head, you should be able to write out that equation. You should be able to understand all the terms in that equation. Okay. On your lab currently, you're doing an error analysis. That just screamed too loudly to me that needed to be a question to do an error analysis. So I'm not going to make you do an error analysis of the big equation, all right? All right, but you know, maybe a portion of it, maybe some of it, you know, some small system or some small equation with a couple terms in it, and just show you go through an error analysis. What else? Oh, real early, probably back the first day in class, we talked about photo interpretation and how you look at a scene and you understand what you're seeing. Okay? So, you know, those sorts of things, you know, how do you do visual photo interpretation? So again, that would be a very conceptual question. And what else was on there? Oh, right. And then, you know, back to the big equation. I want you to really understand it, and I really want you to see how its output or the answer that it can produce really depends on parameters that go into it. What bandpass am I working in? What's the relative spectral response function of my sensor? What's the temperature of my object? What's the reflectance of my target? You know, all those things are going to come into play and produce a final radiance output. And that's going to change depending on you know, what portion of the spectrum you're looking at. Right? So one of the questions that I have in there, I'll you know, be kind of upfront with you, it's computational in the sense that there's some numbers that need to get plugged and chugged through, but the answer that's going to come out is really something that I want you to understand why in one case you might get an answer of 1, in the other case you might get an answer of 5. What is it about the two situations that really, you know, made that true? You know, was it because the bandpass was different? Was it because the spectral response function changed? You know, what was it in the data that was given to you that really made that change? So there's a little bit of computation that needs to go on, but in the end, I want you to conceptually understand why the answers might be different between two sorts of systems. So that's probably about as much as I can say about giving you the question. All right. So with all that sort of stuff in mind, what kind of questions do you have? Oh, as far as materials, make sure you bring a calculator in, you know, just so you can do some algebra, number crunching type computations. But you know, nothing will be too big. But that's all you should do.
No cheat sheet, no formula, no nothing.
No, because in this, it's the only formula that we have right now is the big equation. That's a big equation, but I really want you to be able to come up with that one from scratch. So try it. You know, just literally try it a couple times. Right? Sit down, think about that diagram, write out the equation. Yes, that's the best way to prepare for this. And eventually, it's just becomes so natural to write that thing out.
It's just knowing basically the equation for each of the separate terms, right?
Yeah.
Like knowing what the equation for upwell and knowing the equation for
Yeah, but upwell's easy, right? That's just a term. You know, but okay, I have. Right, so if I start from scratch here, and I know I have the sun, and I know I have to get energy down to my target. So I have my exoatmospheric solar radiance, and I have to go through the atmosphere, so I got a tau. Right? So now I got my irradiance at the surface. You weren't here last time. I went through a whole description of your problem. You're right. Irradiance does change as a function of path. But
I couldn't count, so
no, that's okay. That's okay.
I didn't see the video.
But the distance to here is 150 million miles, or kilometers, and the distance here is 100 kilometers. So effectively, it has no change. All right, but you're absolutely right. It does change based on that difference. And I put a sheet out on the website. Go through that. So you can see it. All right, so now I'm down on the ground. Right, what do I have to do? I have my irradiance onto the surface. Well, I need to get my irradiance in the normal direction. Right, so you got a cos theta with the proper subscript then, and how you're labeling things. And then what happens? And I get reflected from that surface. Well, I got an R, and I want to convert to radians, so I got a pi. Or you put pi over here if you want to. right, well now, I have to go up to my sensor. What happens there? Got a transmission loss, right? So our tau 2. What else happens? Right, you got the multiple bouncing thing going on, so you got a spherical albedo term that falls in there. All right, so now I got my first term. Right, that's my first path. Now you go to the second path. That's the hardest one. Right? Now you go to the second path, which is scattered energy that goes to my sensor. Then I got energy just coming from the atmosphere itself, the upward. Just be able to do the same thing for each. Just go through that exercise in your head over and over again, and this will all become natural. And that's what we want you to know. If you're going to be working in this area, we want you to constantly be thinking about all those terms that are in the big equation and how they relate to one another. So that's what we're doing. So that's why no cheating.
Out of like the chapter 3 and the chapter 4, like radiometry review, what?
I'm not gonna, I'll ask you to do this level of radiometry that we're doing right here. I'm not gonna ask you to
Like
draw.
cross section and stuff.
Yeah.
Okay.
Assume you did all that. And know at Emmett, you tested you on it 12 times, right?
Only ten.
Only 10. Do you have a back problem? Did he give you a back problem on any of the tests? No?
No, reversion now.
Yeah, the Lambertian back problem.
Oh,
Didn't
okay.
do that, huh? Well, that's, you have not had your initiation in imaging science if you haven't had the Lambertian back problem.
We had that problem, but with it back.
Okay.
So what we covered today, that's probably the next test.
Yeah, stuff today is, I don't think, there's nothing today that would be on the test.
So as far as seeing how the output of the big equation depends on the parameters, do you just want us to understand that theoretically, or actually know, like in the visible, this is what matters, this is what doesn't matter, in the near IR, or in the midway IR, actually matter?
All those things come out. Now, here's the reality of it. If you look at, again, we haven't talked about deer sig here yet. We'll talk about that later in the quarter. But one of the things we do in deer sig, which is our synthetic image generation model, is we model all the physics all the time, right? So if I'm working in the visible portion of the spectrum, I'm actually doing the computations in the thermal infrared portion of the spectrum. But their magnitudes are 10 to the minus 28, so they don't contribute anything, right? So in reality, physics doesn't change depending on what portion of the spectrum you're in. If you plug all the numbers in and you do all the physics correctly, the terms will just not matter naturally. Right? They'll be too small to matter. So I would recommend never avoiding the physics because you know it doesn't matter. Keep it in there, do the computation. Sometimes you won't be able to come up with the values that you need, in which case you pretty much have to drop them. But in general, you should be able to come up with good estimates from parameters that you have to use them, and they'll naturally become negligible. So I would say, a lot of times we look at these and we can reduce the big equation down to just a couple terms because we're working in the solar portion of the spectrum. And that's great to do if you have to do a hand computation. But if you're ever doing anything for real, that you're writing a code to predict, every pixel in the scene, I would say to avoid that sort of thing. So, yes, for the test, there'll be places where you can say that this particular thing is negligible. Just make sure that it is. And if you have a slight, doubt, all right, well, I'm at 2 microns. I don't know what I'm doing at 2 microns, because that doesn't naturally, you don't naturally think in that wavelength region. You naturally think in the visible. And maybe you naturally think in the infrared, but very few people naturally think in the middle. So I wouldn't throw away too many terms when you're doing that sort of thing, but you could definitely throw away. If we're working 0.4 to 0.7 microns, you can pretty much throw away the stuff that's out at 8 to 14 microns. So, great calculator, blue books for you. I don't know if you like blue books or not, but they'll be upstairs. And you've got the 2 hours, you've got that room. It's a nice room. I actually think there's a little bit more room in there. So, should have plenty of rooms for that. All right. So I will see you guys on Thursday. If you have any questions, you want to hang out a little later here? Nothing else to do. So.
Did you say you were gonna do something after the break?
What's that?
Did you say you were gonna do something after the break? Oh, the Christmas break?
Christmas break.
Okay.
Yeah.
Not the soccer break.
No, no. Fire drill. That's not cool.